everybody, and welcome to Mindset Learn Extra. It is, of course, a Tuesday. Grade 11s, I'm sure that you are ready because today we do have Tracy, like always. She is going to be doing physical sciences with us. Remember, guys, if you would love to participate on the show, all what you have to do is just to like us on Facebook, www.facebook.com/Learn Extra. Please do tell other grade 11 sciences students to actually tune in because today's topic is actually interesting. Tracy, do you want to tell us what we're talking about today?
Well, today we're actually going to carry on with what we did last week, or what John did with him last week, which was refraction, and we're going to get to total internal reflection, which is really cool because that's how fiber optics work, and so how we get phone signals and telescopes and periscopes and all of those sort of things. It's actually very cool.
Wow, very interesting. So where is this going to help me in the future? Say, for an example, I'd love to, after completing matric, where is this section going to help me in?
You'd probably end up doing it in, if you did any of the engineering degrees, without a doubt it will be part of your physics curriculum. But if you go into, I'm trying to think. Sure, that's just nothing like putting me on the spot, hey. Just in terms of knowing even going into telecommunications and going into any of that sort of field, it's where computers are going. It's how we send information down our computer lines, a broadband, internet, all of that sort of stuff. Not Wi-Fi, obviously, but all of that is all dealt with the fiber optics and internal reflection and stuff. So it's got a very broad application. And doctors use it as well when they use a thing called an endoscope, when they put the things down your throat and they look at cameras, and that's all part of the same thing.
Oh, okay. Yeah. I'm sorry to put you on the spot.
It's okay. It's good for me.
Because the only reason why I'm asking you this is because we have this exciting competition for you guys at home to actually take part in. We have the Future Stars competition. Yes, it's the Future Stars competition for you guys at home to actually enter if you would love to win that great grand prize. So all what you have to do is just to follow us on Twitter and also like us on Facebook, www.facebook.com. That's where you can actually follow the link where it's going to lead you to entering that competition. It's very interesting. So yes, please join us right up until the end of today's show. It is the Grade 11 Science with Tracy. Tracy, take it away.
Thank you. I like the nails, by the way. They match your shirt. I think it's quite very cool. Very dark. I can't wear that color, but anyway, moving on. So, like I said earlier, we're going to look at total internal reflection, but first we need to actually do a little bit of revision. So we're going to go and see what we're going to do is we're going to discuss and define Snell's Law, which you did a little bit of last week. We are going to verify Snell's Law, and you're going to have to forgive me. I broke the laser just before walking in the door. Sorry. And then we need to discuss and define total internal reflection, okay, which is very cool. So first thing we need to remember, and you did this a bit last week as well, is we look at the concept of refractive index. Now this is actually quite important. Remember that when light is refracted, it will go when it changes from one medium to another, so it passes from, for example, if we look, I've got a Perspex block, which I was going to do with you, but when the light moves from outside the Perspex block through into the Perspex block and away from it, it refracts. It changes direction because it changes speed. Okay, and depending on the angle that it hits the block with, will determine what angle it actually ends up moving at. Okay, and if we actually manage to hit the light directly down on the normal, then it will go straight through without changing direction. Okay, that's also why when you look at through blocks like this, like my hand, and I know it's difficult to see the camera, but my fingers would actually look bigger, or they just look like they change shape a little bit through it with this Perspex block. And depending on what type of Perspex this is, it also depends on what you would see, okay? That's all got to do with what we call the refractive index. Every substance has its own refractive index. So we define it as N, okay, that's its symbol, is the ratio, so it's a ratio, it doesn't have a unit, okay, of the speed, C, of light in a vacuum to the speed of the light in the medium, okay? Now remember, what this means is the speed of light in a vacuum is always 3 times 10 to the 8 meters per second. That doesn't change, and essentially it's 3 times 10 to the 8 in air. It changes so little from a vacuum to being in air that we don't actually ever consider it for our purposes, okay? Once it goes into here, it slows down. Remember, It's considered, though there is some debate as to whether this is really the case, but that's far beyond our curriculum, that nothing can actually travel faster than 3 times 10 to the 8 meters per second. Okay, so even your sci-fi movies and like Star Trek and all the rest of it, where they talk about going at, 3 times the speed of light or whatever, we don't think we can actually do that, but that's besides the point. So then we have a whole bunch of refractive indexes. These are constants, okay? They don't change. So A is considered to be 1 because we say that the speed of light doesn't change enough in air, so we leave it as 1 because it's the same thing. Water, 1,33 or thereabouts. Perspex, 1,5. However, that depends on the type of perspex. That perspex, remember, is like a clear plastic. This is a perspex, okay? But it's this one's refractive index is actually 1,25, all right? So it depends on the perspex. Glass is about 1,55. Once again, it depends on the type of glass, how it was blown, its transparency, all sorts of things, okay? And then diamonds have a very high refractive index of 2,4. That's really important for us, okay? And it's the fact that it's got such a high refractive index that we can actually get it to sparkle. Because in a diamond, you get that sparkle from what we're going to look at today, which is total internal reflection. So that's why we love diamonds so much, especially as girls. I'm just anyway, so Snell's Law. Now, you did do this last week with John, so I'm just going to remind you, says to us that when light travels from a medium with a refractive index N1, the 1 is just a label, and it's our first medium, into a material with a refractive index N2, the refracted ray and the incident ray and the normal to the interference between the materials all lie in the same plane. What am I saying there? I can't have, so if I look back here, when I look at this, if my plane is vertical like this, my refracted ray, my normal, my incident ray, everything lies in this plane. Okay, they've got to be either all vertical or horizontal. I'm not going to look at things from an angle. Okay, we're not doing any of that. And then the angle of refraction is related to the angle of incidence by the equation N1 sine theta I. So N1 is your first refractive index, I is your incident angle, equal to N2 sine theta R. N2 being your second refractive index, what it went into, and R theta R being your refracted ray. Remember, unlike reflection, with reflection, your angle of incidence and your angle of reflection are equal. Okay, which is why when we look in a mirror, we can see our images straight back at ourselves, which is great. Okay, and it's always a useful thing to do in the morning before going to school. Okay, and I can tell my boys at school because they have to shave. It's one of our school rules. I tell them I don't think they look at themselves in the mirror because they can't see the fluff, and then they get upset with me. But it's good. They understand.
Yeah, they should.
That's why you've got to look in the mirror. It's important, make sure their hair's all right, and it's a good thing it reflects back at you.
Groom themselves.
Yeah,
yes.
and you're short like me, so if it reflected up, it would be a real problem for us.
Yes,
already.
it will be.
So, moving on. Anyway, refraction doesn't work like that, okay? Your angle of incidence will not be equal to your angle of refraction. That's just the way it works. But there are rules, which you should have done last week as well, with how it refracts. So, if it goes from a low refractive index to a high refractive index, or more optically dense material, it refracts towards the normal. The angle gets smaller, okay? When it comes out again, it gets bigger. Okay, so, wrong way. I did want to demonstrate this to you, but we're going to discuss it, okay? I promise you, I did do this. Unfortunately, I used the wrong color. We're not having a good day. I broke the laser just as we came in, going, I've had my laser for a year, and then I broke it. So my kids will go, that's Miss Fearless. That's the way it works in her classroom. Anyway, so we need to verify Snell's Law, and what we would do is we would take our glass block, which I knew has a refractive index of 1,25. Okay, my glass block. We know this because we need to know these in order to use them at school. It's the sort of thing you should have at school. I put it on a piece of paper and I measured a 30-degree angle. So what we're looking at is we would have our block, okay, and don't forget your normal is an imaginary line drawn 90 degrees to the surface to give us a reference point, and my incident ray comes in like that, and there's my 30 degrees, which pretend you can read. All right, then looking at where it comes out the other side, obviously it's a little more difficult. We use lasers because it's much easier to see. At most schools, and the studio in particular is quite bad because it's so bright that with traditional light boxes, you just can't see the light. So that's why we use lasers. Remember though, and this is really important, never look directly at a laser. Don't point it into somebody's eyes. Don't point it into your eyes. They are very, very dangerous, okay? It'll do damage to your eyes, and you don't want that, okay? So the easiest way is when your block's on the piece of paper, and I really think you should try to do this. It's a good idea. You could do this at home with a square dish and use, put water in the dish, because you know the refractive index of water, and you could probably work it out using that, okay? So get something similar to this. You could do this at home. It's actually quite easy. You point the laser in, make sure you follow the 30-degree line, and then you'll actually see the light come out on the side, okay? Which you would then mark with your pencil, and then you can join the two lines together. Because, so in other words, I would mark that, say it comes out over there, and then I can join those two lines. That now gives me an angle to measure, okay? So it tells me that this angle here, and I did this at home before I came, is actually 23.5 degrees. I can't get more accurate than that. None of your protractors can do that, all right? And even, I'm hesitant to do 23.5 even because, but it was really in between the 23 and the 24. It's probably slightly different to that, but it doesn't actually matter. We've got this angle of incidence. What are we trying to do? Now, there's more than one way to work around this. And I would go, you know, calculating n is far easier than calculating theta, particularly if you're doing math literacy, which is perfectly acceptable, okay? You don't want to have to calculate the angle if you can at all avoid it. And I'm one of those people, I like the easy maths, okay? So this was air, okay? This is my Perspex, or it's a plastic block, and air has a refractive index of 1, okay? So my first n is 1. My angle of incidence is 30 degrees, and my angle of refraction is 23.5. So if I do this, and we're going to use, remember it's sine theta I, and into sine theta r, okay, what I'm going to do is I'm going to calculate n2, because that to me makes more sense, okay? It's also easier. So we know n1 is 1, because it's air. Then we said, well, that was sine 30 degrees, okay? N2 is what we're looking for, and this is sine 23.5, okay? Now we want n2 on its own, so we're going to divide both sides by sine 23.5. Let me just take that away, there we go. So n2, and 1 times sine 30, we all know it's just going to be sine 30. And we're going to divide this by sine 23.5 degrees. Now, I want to show you something on the calculator when you do this. Okay, let's just get rid of what other Tracy was doing. Okay, there we go. Guys, please be careful with your calculator, because if you look, and we're going to go, now we need to go sine 30 divided by sine 23.5. You'll go sine, brilliant, and then you go sine 30, and then what we want to do is we want to go divide by, and we go sine 23.5, and we go equal, and we get some funny number, and we go, but that's nowhere near what I said the refractive index was supposed to be. That's because you've actually inputted it in incorrectly. When you look at the calculator, when you put in sine 30, it opens a bracket. Your calculator thinks that you're taking the sine of 30 divided by sine 23.5. It doesn't know that you want to go sine 30 divided by sine 23.5. So you have to tell it, which means we actually have to do it this way. Sine 30, close the bracket. You're telling it 30 degrees, divided by sine 23.5, close bracket. And we get 1,254, essentially. Very close. Be very careful there, right? It's about how you use your calculator. So we get 1,254. Okay, nice and close. And guys, I think that is a great place to stop. And then when we come back, we'll do some questions.
Oh, yes, guys. Thank you so much, Tracy. We will definitely look into those questions when we come back. Remember to post them on our Facebook page. We'll see you after this. Welcome back, guys. From a short ad break, we are still with Tracy, grade 11s, and we are doing physical sciences. Guys, remember to ask all of your questions because it is important, because Tracy will try and answer all of your questions as far as possible. Remember, our Facebook page is at www.facebook.com/learnextra. And grade 11s, I didn't remind you earlier about this, but it is important that for you guys at home, in order for you to actually be a future star, all what you have to do is just to follow our link on Facebook so that you can enter that exciting and awesome competition. Guys, stay tuned with us as Tracy takes it away.
Oh, thank you, Bummy. So enthusiastic. Anyway, I like that. Okay, so let's do some questions with Snells Law because you're going to get these, okay? Unfortunately, and as much as we hate the trig, it's okay. The nice thing about Snells Law is they really can only ask you in a couple of ways, which is brilliant. So they say to you that okay, let me just extend it this way. Light is passed from air into a rectangular glass prism. Now, in the question, I didn't give you the refractive index because it's actually in the notes if you download them and stuff. But in a test or an exam, you've got to be given the refractive index if you're not working it out. So, in other words, either somewhere in the question, which you'll see in the second question, we've got to state that the refractive index is whatever it happens to be, or there has to be a table with the refractive indexes on. You do not need to learn them. The only one you really need to remember is the fact that the refractive index of air is 1. The rest, you should be given those refractive indexes. And in fact, for glass, we're going to use the refractive index of 1,5, okay? Now they say, what angle of incidence? So I'm asking for theta I. Would give an angle of refraction, okay, theta r, of 10 degrees. Now, unfortunately, sometimes you are going to have to work out the angle. In the last section, before the break, we worked out the refractive index. Nice thing is, we use Snell's law. So, N1 sine theta I equals N2 sine theta r, and it started in air, so that's my initial refractive index. We don't know what theta I is, so let's, okay, ooh, that doesn't even look like an I anymore. Sorry about that. I would moan at my children, so let's write this properly. There we go. And the refractive index for glass is 1.5, and it has an angle of incident of refraction of sine 10 degrees. Okay. Now we need theta I. So first let's get sine theta on its own. So sine theta here, we would divide both sides by 1, so it's actually quite nice because divide by 1, it's the same. Okay, so we have 1.5 sine 10 degrees. Now this is not a maths exam. Okay, in maths, because you're working out an angle, you would now need to use arc sine and sine to the -1 and write down a whole bunch. We don't care. We're just going to be able to use our calculators and get to what theta is, okay? So if we look at our calculators, because I think it's really important you know how to do it, okay, let's just put the calculator over here so we've got the sum in front of us. So to find the angle, we need to use second function sine, okay? So it must say sine to the minus 1. Now it's inside a bracket, and we can say, well, what it meant is we need to go, I'm going to open another bracket, 1.5, which is how I wrote it, times sine 10 degrees. Okay, now I'm going to close my second bracket, and I'm going to press equal. Okay, and we get, let me just check, we get 15,09. And some of you are going, that just sounds like such a funny number. It is. It's okay. Okay. Oh, look, it's disappeared. So we get 15,09. Let's just check back again there. It's 15,098. Remember, it's got to be 2 decimal places. So the 8 would make the 9 move, so it's going to be 15,1 degrees. Okay? So we're going to do another one just to make sure that you can actually set it out. So it's the same concept, but now instead of 10 degrees, we're going to use 36. Same process, okay? So we have sine theta. We're going to do n2, sine theta 2. N is 1. We like it when they do that because it makes our lives so much easier. And this is 1.5. That's what we did in the last one. And sine 36 degrees. Now remember, I can divide both sides by 1, so that gives me sine theta for my incident ray on its own. So let's get theta, okay, because that's what we want. If you want to set it out the way you would in maths, please do that. If it makes it easier for you, you're welcome to do that, grade 11s, okay? I just know that for some of you, you can't remember and it stresses you out. It's fine, okay, as long as you remember how to use your calculator. So let's do this one again. I want sine theta, so let's go through it again. Okay, let me put that here. So, shift, sine, okay. Then I'm going to put the 1.5 in a bracket like it's written, okay. Then I'm going to put, and it's going to be times sine 36. And then I close my bracket again, and I go equal, and I get 61. That's not what I was supposed to get. Okay. I'm hoping there's someone watching the show right now who's going, Tracy, maybe you should read the question. Because now I'm looking at my notes and going, I didn't get that answer. Because if we look at the question, what's the difference? What did I do wrong? The angle of incidence is 36 degrees, not the angle of refraction. So that means, because I'm thinking that's a very strange angle of refraction, it was way too big. So that is incorrect. Let's actually make this, can I make this a bit bigger? Okay, so let's start again, shall we? And grade 11s, this is just to prove to you we're all human, especially teachers, so, well, not really, but we pretend. But we all make mistakes, okay? And please, if you're going to get big angles like that, and that's what made me think, okay, there's something wrong here. That was a very big angle. We don't normally use angles like that, okay? So we know that that's 1. This is going to be sine 36 degrees. This is n 1.5. Okay? Sorry, that should be sine r as well. So we want sine theta r on its own, so we're going to divide both sides by 1.5. 1 times sine 36 is going to be sine 36. Okay. And we're going to divide this by 1.5. So, my angle of refraction. Let's do the calculator again, okay? So we're going to use second function sine, just like we did the last time. Now we're going to put in what we want, what's going to go inside. So it's going to be sine 36. Remember to close the bracket on the 36 so that your calculator knows that's the angle. Okay, so we'll calculate sine 36. Now we're going to divide by 1.5, close our brackets, and we're going to go, okay, much better. And we get 23.7 degrees. Okay, much better angle. Makes more sense now. You guys okay with that? I know this is just a practice thing, and really it's about your calculator work. If you're not confident, grade 11s, please remember that getting to the point where you need to get the final answer, your final answer is worth 1 mark. Everything else up to there, that's where all the science takes place. Okay? And in fact, this first line is the science. That's what I'm looking for. That's what I really want to know you understand. Okay, so let's move on, and we're going to go to total internal reflection just quickly. You have all experienced total internal reflection at some stage, okay? Best example is when you're looking at a pool or you're looking at a lake and you're looking at a body of water and it almost looks like a mirror. Especially if it's a nice calm day and there's no waves and the water's nice and calm, and it starts to look silver along the top. You're starting to see total internal reflection, okay, which is so, so exciting. But total internal reflection can only happen when light is moving from an optically dense medium, like water, for example, to a lower optical dense, like air, okay? Because when my light ray moves from water to air, it gets refracted away from the normal. So we start and we say, here we go. I'm going to use, my light ray comes in here and it refracts away from the normal, okay? If I increase the angle of incidence, so now I do it again and I say, well, let's make the angle of incidence here, okay? My light ray actually refracts a little bit more. So it starts to bend further and further and further away. Eventually, we get a situation where my angle of incidence here is a very specific angle, which then results in my light ray being refracted along the surface, the boundary, okay? This angle here is known as the critical angle. Every single substance has a different critical angle. Diamonds have a very small critical angle. So what happens is often the light gets to this section and then the light rays go against the surface, which is why they shimmer. But what happens when my angle of incidence is greater than this critical angle? In other words, I bring my light ray here. Now it's greater than this angle of incidence. Remember, it's already refracted as much as it can go. It's refracted at 90 degrees, okay? It cannot refract anymore. There's only one place for this light to go, and that is for it to come back in. It now gets reflected. And all the laws we know about reflection, in other words, this angle of incidence will be equal to that angle of reflection, okay? So, what does that mean for us? And so last thing, and then we'll go to a break. 2 things need to happen. Number 1, the light ray must go from a greater optical density to a lower optical density. Water to air, glass to air, something like that, okay? And number 2, the angle of incidence must be greater than the critical angle, okay? And the critical angle is set. It's like the refractive index. You do not need to know what those are. They will be given to you if you need them, okay? You don't need to know them. And if it's greater than the critical angle, gets reflected back in, okay? and the angle of reflection equals the angle of incidence. It's the same as if you go swimming, and sometimes I'm sure you've looked up, if you open your eyes underwater, which I struggle with, but if you look up underwater, sometimes you can't actually see the sky because of the angle of the reflection of the light coming back in. Okay, so it makes life can be quite interesting underwater for looking at things like that, okay? And I think, for me, it's a good place to take a break, and then we'll do applications afterwards.
Oh yes, oh yes, we are definitely going to take a quick ad break. Thank you so much, Tracy. You are making things so much easier. I'm learning so much right here. Guys, if you are learning, please make sure that you tell your friends to actually tune in as well so that they can learn all of this and more. Right now, let's take a break. Welcome back, guys, from a quick ad break. You are still watching Mindset Learn Extra, and I'm your presenter, Pumi, with Tracy in studio. It is a very exciting show. I can see you guys are posting on Facebook. You're asking quite a lot of interesting questions, but we'll definitely be answering those questions. Remember, you can ask them right there on our page on Facebook. It is www.facebook.com/Learn Extra. Remember, guys, you can also be a future star by simply following our link on Facebook so that you can enter and get all of your friends to vote for you. Right now, though, let us just read those questions that you guys have asked, because we promised you earlier on that we will be reading them. Tracy, are you ready for the questions?
We can do that. Let's hit me with it. Let's see how we go.
Okay. We have a Facebook message question here from Dumisang Bukaba Wamutswana. Do you always use sign for all the calculations?
Yes. Now, I know that sounds like quite a silly question, but it's actually not, and I know where it's coming from. When you did Newton's Law earlier this year, and you looked at things on slopes and stuff, and you looked at components, sometimes we used cos, sometimes we used sine, but that was just because of the components. We use sine here because that is the law, okay? And that the whole equation where we relate n1 and n2 with the sine theta I and theta r, that was proven experimentally, okay? So it is always sine. There's absolutely no exception to that one.
Oh, okay.
No exceptions. Yeah.
Oh, nice. We've got two more questions again. We have Shaisega Theodore wanting to know, my question is, what is a Snell's Law?
Okay, sweetie, Snell's Law, and I'm just going to go find it again where we put it, is, here we go. Snell's Law is a law, okay? So it's like Newton's law of universal gravitation or Newton's first law of motion, any of those laws. It was done by a scientist called Snell. I don't know what his first name was, okay? And it's a law that gives us the relationship between the amount of refraction and the incident ray, depending on the refractive index. So depending on what the materials are, okay? So your textbooks might have worded it slightly differently, but it's all the same, okay? When it says, so when light travels from a material with a refractive index N1 into a material with a refractive index N2, the refracted ray, the incident ray, and the normal to the interference between the materials all lie in the same plane. The angle of refraction, theta r, is related to the angle of incidence, theta I, by the equation that we've got, okay? So we can state it as an equation, which is n1 sine theta I equals n2 sine theta r, okay? Or we can state it in words, but it's a law that you have to learn, okay? It's just it's one of those, unfortunately.
Okay.
Yeah.
Okay. And one last question that we can possibly read right now. From the calculations that we did earlier, Razia Amin wants to know, hi, Mindsetters, where did Tracy get 23,5?
Okay, sweetie, that was the whole issue of me breaking the laser. Okay, and unfortunately, and I know my producer's about to kill me, but actually you can't see it because it's in pencil, but on this piece of paper, I did the experiment before I came into the studio, okay, because I needed to make sure that it worked, which is the first thing, and then I broke the laser. So when I did the experiment, okay, and I looked at verifying Snell's law, which is what we did here, I measured the 30 degrees because I wanted to know what the angle of incidence was, and I wanted to make sure I got it at 30 degrees. So it made it, because you need to know where we're starting from. And then I actually have and Pumi can actually verify it, really is there, I promise.
Yes.
Okay, I found the refracted ray, so I found where it went, and then I measured that angle of refraction. So that's where the 23.5 comes from. It's experimental. So it wasn't something I expected you to know, because what we were doing is proving that the refractive index for my block was 1.25. Okay, so I measured it. And if you go and do this at school or you do it at home, you might not get 23.5, even if your angle of incidence is 30, because the refractive index will be different of your material. Okay, so that's where it came from, is that it's an experimental value that I actually found. Okay, and that brings us to the whole thing with Snell's Law. Getting to the equation, now we're lucky because we just have the equation and off we go. But it would have been found by hundreds of experiments, lots and lots and lots of experiments. And then they would have found this relationship mathematically, trial and error, all sorts of things. So it's quite an involved process. Lucky for us, now we don't have to reinvent the wheel, yay, and we can just actually go ahead and do it and verify it really, really easily, which is actually great for us. Okay, but now, are we okay with questions?
Oh,
so
yes, we are.
Okay. Quickly, we need to move on to, now, we spoke about total internal reflection. I told you why we need it, when it happens, but why is it important? Well, if I take a right-angled triangle, so we have one over here, but let's make sure we can actually see it, because if I do it in black, no one's going to see it. Okay, so here's a right-angled triangle. Okay, the inside's white, it doesn't matter. When whether it's glass or perspex, if I take a right ray, okay, let's use this one, and I hit it along the boundary. When light hits a glass block or a prism or anything at 90 degrees or at 0 incident angles right along the normal, it will slow down, but it will not change direction, so it goes straight through. At this point, we now have, we would now need to know where the normal is. So the normal is at 90 degrees, that's close, but with a 45-degree triangle, and what I mean by a 45-degree triangle is that angle there is 45, okay, that one is 45 or thereabouts, and this is 90 degrees. We have to have a 90-degree triangle, okay? And then those two have to be 45, actually. It's an isosceles triangle. This angle of incidence over here is now greater than the critical angle. And what that does is it causes this light ray to now be reflected. So instead of light coming out of the block, my light actually now comes down like this. Okay, and it's another thing you can do quite easily at home if you have a right angle prism. And now we get a reflected angle. And the angle of incidence is equal to my reflected angle, okay? What's nice about this is that it always results in my light that comes out going through the bottom end of the prism at 90 degrees, okay? Because it's a 90-degree triangle. So it makes life so much easier, okay? So it's a nice isosceles triangle, but why do we want to know? Why is this important? It's applied in a lot of things, okay? So the first thing we're going to look at is that it's applied in things like periscopes. Now, periscopes seem quite not really part of our everyday lives, but it's what submarines use, okay? I'm sure you've seen a movie at some stage where you're in a submarine and the captain says, up with the periscope, and a thing comes up out of the floor, and he opens things up and he looks through, and he can actually see what's happening above the ship, okay? Submarines don't have windows, okay? So they can't see through a window, and besides, they're underwater, it's too dark there anyway. But the periscope literally has a set of prisms and lenses, because we want to make a good sharp image, and it's got to work a little bit like a telescope, make something far away look like it's close. But what actually happens, okay, is my sea captain is sitting over here. Now, please don't laugh at my drawings, just pretend. Okay, and this is his eye. Okay, there's his eye. He's got a green eye. It's great. He's looking over here. Okay, what he's looking at is over there. Now, the light comes in from the objects. We only see objects because we reflect light away from us. Light comes in, travels to the first prism, 90 degrees over here, great. Total internal reflection happens, but now it goes straight down. He's not looking at the bottom. He's looking on the side. So we take another triangle, okay, another 90-degree triangle. Once again, greater than the critical angle, and we cause it to deflect into his eye, okay? You could build your own periscope. One way to see around corners, okay? You could build this really, really simply. It's not that difficult. We use prisms instead of mirrors because it gives us a clearer image. We could do the same thing with a mirror, okay? If we placed mirrors in exactly the same, so if I put a mirror here and a mirror here, I could do exactly the same thing with the lights. I can bend it in exactly the same way. But prisms help us get a sharper image, okay? It's much, much better, though you could use mirrors. And remember, with periscopes, we need to be able to see far, far away, okay? So the whole point with a submarine is they go underwater, deep depths, and then they're in the middle of the ocean, and they want to see far away from where they're at, okay? So they need to have a lens system to help. Mirrors don't help with that very well, okay? Your prism system helps better. Another place that we use it is binoculars. Okay, now remember, binoculars are great if you go out in the bush and you're trying to find animals, or if you go and watch, say, a soccer match and you're sitting far up in the top of the bleachers and you can't see anything. Binoculars are great. This is only one half of the binoculars, okay? Now, the person, their one eye is over there at the top. This is what they're looking at. And it's the same concept, though. Look at the way we've arranged the prisms, okay? Here, we've arranged the prisms so it gets reflected twice, because that's what we need. We don't want it to be reflected once, but twice. Binoculars need to be quite close, okay? Because this is only one eye section, and we need to have two of them, okay? So we need to have them squashed in. So the prisms overlap, okay? My diagram got a little bit squashed, but that's okay. My light comes in, 90 degrees over here, so it's not going to change direction when it hits the prism. Gets to my first corner, the next side, okay? Greater than the critical angle, total internal reflection. Gets to the next side, can you see it doesn't hit it at 90 degrees, total internal reflection again, then it comes out. And the same thing happens before it goes into your eye. Once again, I suppose we could do this with mirrors, but that would just be stupid in a pair of binoculars, first of all. Your glass prisms give you better images, okay? As with the periscope, there would be a lens, okay? You're going to spend more time on optics later on, okay? I think in grade somewhere along the line, I can't remember where, but you would put a lens in, okay? And that lens changes how big it is, how small it is, all of that sort of stuff. No, you did that last year. We did the lenses last year, okay? But now the thing I know you're waiting for, fiber optics. Now, fiber optics are wonderful. They're just the most incredible invention, okay? What happens with fiber optics is it's a very, very thin cable, okay? Perspex, plastic, all of those sort of things. Sometimes they're glass, okay? Very, very thin glass. And light is entered at one part of the cable, and then it bounces off the cable because it never gets to a point where the angle of incidence is smaller than the critical angle. So it keeps bouncing off the edges, which is great because it also means, for example, with data, when we telecommunications, data travels along these cables at 3 times 10 to the 8 meters per second. How amazing is that? That is so, so quick. It's better than analog, okay? Also, very little is lost. The light, the way the cable is shielded, okay, prevents the light from leaving it, okay? Fiber optic Christmas trees, best invention in the world. My friend in PE has one, and I love it when they put the lights on because it changes color and the ends all glow, and it's all this because the way the tree's set up and the lights form through it, okay? Fiber optic cables are beautiful to look at. In your telephone system, there are millions of fiber optic cables which then transport information, okay? And I know it's a little to go, hang on, wait, how can light be information? Don't stress about that because there is a process where we convert digital information, electronic information, sound information into light pulses, okay, which then gets converted again later on, okay? And in fact, using fiber optic cables, like I said earlier, besides telecommunications, things like endoscopes, very, very important medical diagnostic tool. And what an endoscope basically is a tiny little camera, okay, which a doctor can use to do what we use keyhole surgery. In fact, I had that done on my knee 2 years ago, where instead of having to, and I had to have all sorts of things done to my cartilage, and instead of the doctor having to open up my knee and give me long, big scars everywhere, they put a little pinprick, put this tiny little camera through, and you can see exactly what's going on, and then they can fix it, okay? Or if they want to see if somebody needs open heart surgery, they can use an endoscope, and they can actually go into the heart, look at the heart's arteries, look at what it looks like, without actually having to do major surgery to start off with, because it's a tiny little camera which then sends images back on these tiny, thin little wires, which are fiber optic wires, okay? Which makes our lives so, so, so much easier. All right? Okay. Pumi, before I do anything else, no more questions? Is everyone okay?
We only have a few comments here.
Okay.
A lot of people are loving the show. Thank you so much. Thank you so much.
You guys can watch it again next week. I like it.
Oh, yes, yes. You can actually watch again next week. Tracy will be here bringing you nothing but the best. And, of course, with a new and exciting topic for you at home to actually go through. There's quite a lot of, I've read 2 comments here where some learners are feeling like they left behind. You know, what advice would you give to them, you know?
Download the notes, guys, because the notes are actually quite extensive, all right? And then read through them again, and then check with your textbooks as well. Obviously, there's not everything I can do. I can't do absolutely everything with you because we only have an hour.
Oh, yeah.
And, you know, it's perfectly normal to feel like you've got a little bit left behind. Unfortunately, we do have a short period of time, but you know, you can watch the show again. So remember, you can get it off the website in the next couple of days, so you can always watch the show again, download the notes through the links, and then use those as reference, and also do a little bit of your own research. I mean, we're talking about fiber optics and cables and stuff, and in fact, South African television, the fact that you're watching that's coming to you through fiber optic cables. Okay, the whole way that is done, that whole digital revolution is coming from that. And in fact, South African television, even public television, has to go that way because that's the way the world's going. When it comes to making international phone calls through landlines, it's all through fiber optics. So these things are just really important to our everyday lives without us actually realizing. I mean, we like the pretty lights when we see them on Christmas trees and all the rest of it, but actually, we don't realize how much it is. When I phone my best friend who lives in Port Elizabeth on my landline, it's using fiber optic cables, which is why I can get a nice clear signal. In fact, sometimes I prefer that to my cell phone because I can get a nice clear signal. When I phone, I have family overseas. The fact that we have fiber optic cables means I can phone them and feel like I'm in the same room as them. Sometimes there's a bit of a delay, but that's a distance thing. But it's so nice because it's so important, and it's all got to do with the fact that light hits the cable at an angle greater than the critical angle and gets reflected back, and it bounces all the way along.
Oh, yeah.
Yep.
That's actually the beauty of science. I mean, we see these things every day and we ask ourselves, where does this come from? But it really does come from the beauty of science. Guys, Tracy can actually answer as much questions as she can, but do remember that we are always on Facebook and we can actually answer your questions even after the show. So nothing should stop you from liking the page or asking your friends to like the page and ask their questions, because, you know, at the end of the year, you know, they might refer back and want to know what is really going on, especially when having to revise their work and everything.
Absolutely.
Yeah. In any case, guys, I think we have come to the end of today's show. Please do remember to catch us again next week, same time, same place, with Tracy, of course. Yeah, any advice, any last word?
Keep studying.
Keep studying. It helps. Bye-bye.